Hi, I am researcher Nye. You may have heard of the various models of generative AI and the sort of amazing things they can accomplish. Ever wonder why they can do their tricks? Here we are going to explore how some of them work and in what ways they can help, or prevent, the delivering of knowledge we need. First, we have the Generative Adversarial Networks, or GANs. GANs are deep learning architectures typically composed of a generator and a discriminator working together to generate accurate data. The generator network takes in a random input and generates a new output, such as an image or audio clip, that tries to mimic some real data. Then such output is combined with a batch of real data to form a training set. The discriminator network takes in the training set and outputs a probability for each instance in the set to classify it as real or generated. The correctness of such is used to train the discriminator. The updated discriminator will then classify a new set of real and generated data, and the generator is trained based on how well the generated data can fool the discriminator and get classified as real. The whole process repeats so that the generator and discriminator get better and better. GANs have been used for image and video synthesis. They can generate realistic images of faces, objects, and even landscapes. They can generate a high-quality version of a low-quality image or remove noise from images. GANs can also generate new video frames that follow the same pattern as the real video. Further, GANs can be used for data augmentation by generating new samples similar to the real samples of a data set but different enough to provide additional training data. This can be helpful in situations with limited data available for training a deep learning model. However, GANs can be challenging to train and require much computing power. They can suffer from mode collapse, where the generator produces a limited set of outputs and fails to capture the full range of possibilities. They can also produce unrealistic or unrepresentative data, which can negatively impact the performance of other AI models. Next, we come to the generative model of variational autoencoders, or VAEs. VAEs are a type of generative model that combines concepts from conventional autoencoders and probabilistic latent variable models. Simply put, a conventional autoencoder consists of an encoder, decoder, and latent representation. The encoder E takes the input, X, and maps it to a point Z in the latent space as its representation. The decoder D then takes C as its input and outputs X prime, which is a reconstruction of the input X. VAEs have a similar architecture, but the encoder of a VAE maps input data to the parameters of a probability distribution, that is, mean and standard deviation, in the latent space instead of fixed data points to capture the essential features of input data while facilitating the generation of diverse outputs. Then, the decoder takes samples from the latent space and reconstructs the input data. It plays a crucial role in generating diverse and realistic outputs. VAEs are widely used for generating realistic images. They can learn latent representations of images and generate new, unseen samples. Then, by learning the distribution of normal data, VAEs can detect anomalies or outliers in a dataset. They can be employed for filling in missing data in a dataset by generating plausible values based on learned latent representations. They can also be used in creative applications for style transfer, generating images with different artistic styles. Nevertheless, VAEs may struggle to capture complex data distributions or the global structure of the data effectively, leading to challenges in generating highly realistic outputs. And like GANs, VAEs can also experience mode collapse, where the model generates a limited set of outputs, missing diversity in the generated samples. If the previous models sound unfamiliar to you, I bet you should have heard of the diffusion model. The idea of this is to systematically and slowly destroy the structure in the input data through an iterative forward diffusion process. We then learn a reverse diffusion process that restores the structure, yielding a highly flexible and tractable generative model of the data. Hence, for an image as input data, the forward diffusion process of the diffusion model is a process of turning the image into noise, and the reverse diffusion process is supposed to turn that noise into the image again. An image has some non-random distribution of color pixels. Now forward diffusion is to destroy such distribution in multiple steps, with a random distribution, that is a noise added to it in each step. At the end, we should have something similar to pure noise. Conversely, reverse diffusion is to convert pure noise back into an image. This is done by using some neural network similar to the generator network of a GAN, but our network will have an easier job because it doesn't have to do all the work in one step. Instead, it will do that in multiple steps by removing some noise at each step. The diffusion model can be applied in various ways. In text-to-image and video generation, the input will be some text prompt and corresponding image and video will be generated as output. It can be used in creative content generation, product design and visualization in manufacturing, visual production for education, training and entertainment industry, and automated product features demonstration. Diffusion is also a powerful technique for modifying or transforming existing images using the text prompt, doing image-to-image transitions. For instance, we can convert crude hand-drawn or unfinished images into beautiful pictures with the same content, or provide an input image of a fashion model and change the look and feel by changing the color and style of the apparel automatically. But deploying diffusion models can be challenging. They are computationally intensive, involving lots of processes and require significant resources, which can be a hurdle for real-time or large-scale applications. Additionally, their ability to generalize to unseen data can be limited, and adapting them to specific domains may require extensive fine-tuning or retraining. Also, the complexity of diffusion models makes them difficult to interpret, posing challenges in applications where understanding the reasoning behind the output is crucial. Finally, we will discuss the transformer model, upon which the popular ChatGPT or Chat Generative Pre-trained Transformer was built. The transformer model is one of the most exciting recent development in GAI. It can be used to write stories and essays, answer questions, translate between languages, and chat with humans. It is very good at keeping track of context, and this is why the text that it writes makes sense. But how exactly does a transformer work? Imagine that you're writing a text message on a phone. After each word, you may get 3 words suggested to you. For example, if you type "Hi, how are," the phone may suggest words such as "you" or "things" as the next word. If you keep on selecting the suggested words, you'll quickly find that although it may make sense when you look at each set of 3 or 4 consecutive words, the whole batch of words doesn't add up to anything meaningful. Why is it so? It is because the model used in the phone doesn't carry the overall context of the message. It simply predicts which word is more likely to come up after the last few. Transformers, on the other hand, keep track of the context of what is being written, making a more informed choice of words, and therefore the text they write makes sense. Now that we know what transformers do, let's check out their architecture. The transformer architecture has an encoder and decoder layer that consist of 4 main parts: embedding, positional encoding, transformer blocks, and softmax. Among them, the transformer blocks are the most complex of all, and many of these can be stacked together to form a large unit. For embedding, you first have to do tokenization. It involves a huge library of tokens corresponding to all the words and punctuation signs used. The tokenization step takes every word and punctuation signs in the input sentence and converts it to the corresponding token in the library. Once the input is tokenized, it will be turned into numbers by embedding, which is simply the converting of each token to a vector or a long list of numbers, such that if 2 tokens, or words, are similar, the numbers in their corresponding vectors are similar to each other. Otherwise, the numbers are different. Positional encoding consists of adding a sequence of predefined vectors to the embedding vectors of the words to show their positions in the sentence. This ensures that sentences with the same words in different sequential order will be assigned different sets of vectors to represent them, carrying information about the word position. Now, the next step is to predict the next word following the input sentence. This is done with the encoder and decoder, consisting of transformer blocks, trained precisely to predict the next word in a sentence. Each transformer block is formed by 2 main components, the attention component and the feed-forward component. The attention component deals with the problem of context. Sometimes, as you may notice, the same word can be used with different meanings. This tends to confuse language models, since an embedding simply sends a word to a corresponding vector, without knowing which definition of the word it's using. Here, we employ the technique of attention to help language models understand the context. To understand how attention works, consider these two sentences. As you can see, the word ticket appears in both, but with different definitions. In the first sentence, we're referring to the permit to enter a venue, and in the second to the legal notice of a traffic offense. But the machine doesn't know that, so we have to tell it by using the other words in the sentences. In the first one, the word concert tells us that we're talking about the permit to enter a venue. Similarly, in the second one, the word police tells us that we're talking about the legal notice of a traffic offense. The function of the attention component is to move the related words in a sentence closer in the word embedding. As such, the word ticket in the first sentence will be moved closer to the word concert. Similarly, in the second sentence, the word ticket will be moved closer to the word police. That way, the modified word ticket in each of the two sentences will carry some of the information of the neighboring words, adding context to it. Meanwhile, the feed-forward component is used to project the attention output, potentially giving it a richer representation. So, by the transformer block, the encoder produces a representation of the input sentence, with context as output. This is fed into the decoder, together with all words the transformer has generated so far that follow the input sentence, to form a longer sentence. The transformer blocks in the decoder will attend to all these and help output scores for all the words used, where the highest scores are given to the words that are most likely to be the next joining that longer sentence. The last step of a transformer is a softmax layer, which turns these scores into probabilities that add to 1, where higher scores correspond to higher probabilities. Then, we can select the probability that is the highest, and the corresponding word is the output that the transformer generated. After that, we repeat the step. We now feed the input sentence through the encoder and the output generated through the decoder into the transformer, and generate the next word. Repeating this step again and again, the transformer will end up writing a whole passage. Transformers are primarily used in natural language processing and computer vision. In fact, any sequential text, image, or video data is a candidate for transformer models. Transformers have had great success in language translation, speech recognition, and time series prediction. Pre-trained models like GPT-4 and BERT have demonstrated the potential of transformers in document summarization, text generation, and video understanding. Due to the wide adoption of transformers in computer vision and language modeling, they have started being adopted in new domains like medical imaging and healthcare. Researchers are utilizing transformers to gain a deeper understanding of the relationships between genes and amino acids in DNA and proteins. This allows for faster drug design and development. Despite their strengths, transformers often struggle with common sense reasoning, as the attention process primarily relies on frequent patterns learned from open data rather than true understanding. So they may find handling rare but obvious events difficult. They may also inherit any bias present in the open data, leading to unfair outcomes. As transformers, commonly involving millions of parameters nowadays, are difficult to interpret, it is a challenging task to understand why they make certain predictions and make improvements on their shortcomings. So we have covered some of the popular GAI models here, and hopefully you could appreciate the impact they could make on our future applications. We will continue our exploration in the next episode. See you soon.